Welcome to Hartman Math. Before we get to hyperbolas, a little review of ellipses. Go ahead and pause here, work through the two problems. All right, for our first one, we're going to want to get this into standard form for an ellipse. So it's going to have to do with completing the square. So we're going to group the x's, group the y's, move the constant to the other side, and factor out the leading coefficients. After we do that, we're going to add 4 to complete the square here, add 1 to complete the square here, and to balance, add 36 and 2 from distributing, and that makes 38. We're going to add that to the right side to keep our equation balanced. We're going to write these as squares of binomials, and then ultimately, since it's equal to 18, we're going to divide both sides by 18 so that we get it equal to 1. Once it's in standard form, we can identify the center as 2 comma negative 1, and a as 3, and b as the square root of 2, and the foci would be from c, and c squared is equal to a squared minus b squared, so c squared is going to be the 7, and c is the square root of 7, and since it's vertical, since the bigger denominator is under the y, we're going to go up and down the square root of 7 from that center. So our foci, 2 comma negative 1 plus or minus square root of 7. Remember the eccentricity is going to be c divided by a. That's our eccentricity. What about the eccentricity of the Earth's orbit? Well, that is in the textbook. That's about 0.0167. And remember, anything if it's close to 0, it's going to mean it's very circular. It's lesson 10.4, hyperbolas. You can see the definition for a hyperbola is almost identical to that of an ellipse, with one major difference. Instead of the sum of the distance being a constant, now it's the difference being a constant. And if we're looking at general form for a conic section, and assuming that b is 0, because otherwise if b is not 0, then we get our hyperbola tilted. That's pretty complicated. But if that doesn't happen, then we know if a and c are opposite signs, we're going to have a hyperbola. And a hyperbola is what happens when we take our double napped cone and we slice it perpendicular to the base. We're going to get a branch here and a branch here, and that's our hyperbola. And the picture to represent the definition is here. Take the two distances and subtract them, and take the absolute value so it remains positive. That's going to be a constant. And then the mathematical picture is that we have vertex here and here. Those will be the 2 points on the branches that are closest to the center. And we've got these points here. They're really unnamed, but you'll hear me refer to them as box points. And that's a distance of a to the vertex, b to the box point from the center, and then c to the focus. The focus is going to lie inside the branches. It's going to be farther away from the center than the vertex. The segment that connects the two vertices is called the transverse axis. That's going to be what's going to determine this. It's going to be horizontal. Horizontal transverse axis opens to the sides. Horizontal. Our equations for the horizontal, x minus h squared over a squared minus y minus k squared over b squared equals 1. So very similar to ellipses, with just instead of a minus being a plus. Remember our equation. And then if it's going to be a vertical transverse axis and open up and down, y comes first. A squared is always the first denominator. So that's how we identify the vertices and what a is. If x squared is positive, a squared is under that. It's going to be horizontal. If y squared is the one that's positive, it's going to be vertical. A squared is the first denominator. C squared equals a squared plus b squared. It looks identical to the Pythagorean theorem. In fact, it comes from the Pythagorean theorem. But this time, our picture is if we pull off this length here, which is the C, distance from center to focus, and pull that off, it fits perfectly right here. So a squared plus b squared equals c squared. Pythagorean theorem. And again, if we're lucky enough that our center of the ellipse, h and k, is the origin, it just simplifies here. Example number 1, find the standard form equation, hyperbola having foci and vertices. Let's go. So again, good idea to have graph paper. Plot your foci. Plot your vertices. How do they line up? They line up vertically, which means as far as an equation goes, y is going to come first. Now we're looking for the center. Well, the center has to be the midpoint between these 2 points or these 2 points, the point directly in the center. Or we could just look at the graph, or you could use the midpoint formula. You're going to find out it's negative 1, 5. So there's our h. Be careful on the order here. A lot of times we just kind of default to x, y, but it's reversed this time because of it being vertical with the y first. H, k. We go in there. So A is the distance from the center to a vertex. That's going to be 2 units. B we don't know, but C we know. C is the distance from our center to a focus. That's going to be 4. And C squared equals A squared plus B squared. So A squared is going to be 4. C squared is going to be 16. 16 equals 4 plus our B squared. It's going to be 12. I think that's going to be all we're going to need to know for our equation. We got our H and our K. A squared is going to be 4. B squared is 12. There's our answer. Example number 2, let's sketch a hyperbola. Given a pretty basic one here. Identify the foci after we're done sketching it. It's not in standard form. It's got to equal 1. So let's divide everything by 36. We got no parentheses, so the center is going to be the origin. What is A? Unlike ellipses, A comes first. This is A squared. So A is going to be 2. It came from under the X, so it's going to be left and right 2 units from the center. B is going to be 3. That's B squared. Second denominator for hyperbola. That's always B squared. So B is going to be 3. Go there. So vertices. Box points. Draw the box. Dotted. Through the vertices and the box points. Then through the corners of the box, draw the X. Probably a little bit longer than I've drawn here, because these are the asymptotes. The branches of the hyperbola are going to get close to these asymptotes. The branches have to pass through the vertices. So we're going to go through here and get close and get close. We're going to go through here, close and close. Those are the branches. Make sure they, as we sweep away from the center, it keeps getting closer and closer. So our foci, C squared equals A squared plus B squared. 4 plus 9 is 13. So C is the square root of 13. We're going left and right because we're horizontal. So from 0, 0, left and right root 13. Foci are going to be plus or minus root 13, 0. Asymptotes of a hyperbola. Okay, the book likes to give them in this form. I don't really like them in that form. It's true. I really much prefer the point slope form. Y minus y1 is equal to m times x minus x1. All they've done here is did the same thing, but just added the k over. Either way is really fine. Same thing here. Now, they're saying that the horizontal one, your slope looks like this. The vertical one, your slope looks like this. I don't know if it's worth it to try to memorize that, because it could be very easy to get them mixed up. I think that it's going to be best for us to figure out the slope in the context of the problem or by looking at a graph. Example number 3, sketch the hyperbola and find the equations of the asymptotes. Okay. So we're going to group x's, we're going to group y's, we're going to remove the constant. And notice, the y squared, that's the one that's positive, so that's probably going to go first. The x squared one, that's the negatives, that's going to go second. Careful how we group, because I pulled the negative outside, which means I factor out a negative here and here. So careful with that. Okay. If for whatever reason this came out to be negative, we would need to divide by a negative, and it's probably going to switch these. I don't think we have that situation here. Let's factor out a leading coefficient and factor out a leading coefficient. Let's complete the square. Add a 1, add a 9. When we add a 1, we really added 4. When we added a 9, we really subtracted 81. Now, so we've written each of these as binomial squares. Got to get it equal to 1. So let's divide both sides by 144, reduce our fractions. And that's going to be the most important part, getting it into standard form, because that's where all the information is. We got y minus 1 squared over 36 minus x plus 3 squared over 16. That's going to equal 1. That's our standard form. I want to be able to sketch it from there. We've got a center at negative 3, 1. So again, led us to here, as there's our standard form equation. Center is at negative 3, 1. Vertex, under the y, up and down 6. Box points, under the x, left and right 4. Draw the box. Draw the x, draw the asymptotes. Okay, be safe, make those asymptotes nice and long. Now, where do the branches go? The branches pass through the vertices. The vertices are here and here. Y came first, so we know it's got to open up and down. So pass through, get close to, approach those asymptotes. We've got our sketch. Now, what about the equations of the asymptotes? We want to use point slope. We want to use the point as the center. Negative 3, 1. So y minus 1, kind of looks like this, is equal to. Now what about our slope? If we're looking at the graph, we're just going to go rise over run. Up 6, right 4. So that reduces to 3 over 2. Now there's one that's positive, there's one that's negative. So we'll say y minus 1, not squared, we're talking about lines. Y minus y1 is equal to m times x minus x1. So y minus 1 is equal to plus or minus 3 halves times x minus negative 3, which comes out as x plus 3. And the book would maybe add a 1 and likes to add it right there. That's fine, but this is also fine. Now, what if we weren't looking at the graph? What if we just had to come up with this and we didn't want to bother with the graph because it hadn't asked us to graph? We can get the information from the equation and not having to memorize. Is it b over a? Is it a over b? Okay, because slope is rise over run. Rise over run. Rise is y, run is x. Rise, run. So whatever comes from under the y, that's your numerator. Whatever is under the x, that's your denominator. 6 over 4 reduces to 3 halves. So we can get it from the equation as well. Example number 4. Find the standard form equation of the hyperbola, It's got these vertices and these asymptotes. Let's go after the center. The center is the midpoint between these 2 points. That's got to be 4, -1. Which kind is it? If we line this up, 0, -1, 8, -1. Horizontal. That means x comes first for a hyperbola. We've got our h, we've got our k. We've got a, I think. A is going to be the distance from the center to a vertex. So a is going to be 4. That's easy. What about the b? That's where it gets a little challenging here. Because all we have is this other information about the asymptotes. So again, is our slope's 1/2 or -1/2, and kind of just focus on the 1/2 there. We're talking about horizontal. So what's the slope going to be? Once again, think rise over run. Under the y is rise. Under the x is run. Rise over run. It's going to be b over a. b over a will equal 1/2. Now, that does not mean that b is 1 and a is 2. It just means they're in that ratio. This could be 5 and this could be 10. Okay. But we do know actually a, we've already figured out, is the distance from the center to the vertex. That's going to be 4. A is 4, and then we can solve for b. So since a is 4, b is going to have to be 2. So that's all we really need. A squared is going to be 16, b squared is going to be 4. Final answer, x minus 4 squared over 16 minus y plus 1 squared over 4 is equal to 1. And that's it for today. I'll see you next time.